This presentation is an introduction to the SiPM. The SiPM, or silicon photomultiplier, is a solid-state sensor which has a high gain achieved at low bias. It has single photon sensitivity from the near UV to the near infrared, with a peak detection efficiency of around 50%. This presentation will give a brief introduction to the SiPM structure and operation, starting with a description of the Geiger mode and SPAD sensors, and how a summed array of SPADs becomes an SiPM. Finally, I'll talk about the SensL fast output and give some suggestions for finding further information on the subject. We start our introduction by considering a simple photodiode. When a photon is absorbed in silicon, it will create an electron-hole pair, and the reverse bias applied to the photodiode sets up an electric field that will cause these charge carriers to be accelerated towards the terminals, resulting in a flow of current. If, however, the applied reverse bias is set at a point beyond the breakdown voltage of the diode, then the diode is said to be operating in the Geiger mode, as indicated in the current voltage plot here. When a bias in excess of the breakdown voltage is applied to the diode, an avalanche region may be formed at the PN junction. Any charge carriers in this region will now be accelerated to such an extent that they will generate secondary charge pairs through impact ionization. Each of these new charge carriers will also generate further ionization, creating a self-perpetuating ionization avalanche that spreads throughout the silicon volume subjected to the electric field. The silicon will break down and become conductive, effectively amplifying the original electron-hole pair into a macroscopic current flow. Therefore, this type of photodiode is referred to as a SPAD, or single photon avalanche diode. A SPAD that has been triggered by an interacting photon will continue to generate current until it is stopped or quenched in some way. Without quenching, the SPAD would be unable to detect subsequent photons. Quenching can be achieved through the use of a series resistor, RQ, which limits the current drawn by the diode during breakdown. Looking at a simplified current voltage plot, we can illustrate the different stages of the avalanche process. A detected photon causes a breakdown and a large current flows. This results in a voltage drop across the quench resistor, which in turn reduces the bias across the diode to a value below the breakdown, therefore lowering the internal electric field and stopping or quenching the avalanche. The diode then resets itself by recharging back to the bias voltage and is available to detect subsequent photons. In this way, each detected photon results in a cycle of avalanche, quench, and reset, with the SPAD functioning as a photon-triggered switch. This switch is either in an on or off state, resulting in a binary output. However, regardless of the number of photons absorbed within the SPAD at the same time, it will produce a signal no different to that of a single photon, and so the sensor is not capable of giving information on the magnitude of the incident photon flux. To overcome this lack of proportional information, the silicon photomultiplier integrates a dense array of small independent SPAD sensors, each with its own integrated quench resistor. Each independently operating unit of SPAD and quench resistor within the SiPM is referred to as a microcell. Here we see a close-up image of a microcell from a SensL SiPM. Here we've replaced the image with a cartoon of an SiPM layout. It shows the active areas, the quench resistors, and the metal tracking. The resistors and tracking result in a dead space between the active areas. Therefore, each SiPM will have a fill factor that varies with the microcell's size. Now let's consider the output from an SiPM. When a microcell in the SiPM fires in response to an absorbed photon, a Geiger avalanche is initiated, resulting in the same cycle of breakdown, quench, and reset as we saw for the SPAD. The output signal caused by the firing of this microcell is available from the anode or cathode. Each microcell detects photons identically and independently. During a microcell's avalanche process, all of the other microcells will remain fully charged and ready to detect photons. If two microcells are triggered simultaneously, then the sum of the photocurrents from each of these microcells combines to form an output twice the size of a single microcell. In this way, the SiPM is capable of giving information on the magnitude of an instantaneous photon flux, with an output proportional to the number of triggered microcells. The response from each microcell is very uniform, and the individual photon levels can be very clearly observed, as in the scope trace here. As well as the single photon level, the discrete levels corresponding to 2, 3, and 4 detected photons are also clearly distinguished. The corresponding charge histogram also shows the photon numbers clearly defined. So, we've seen the structure of a conventional SiPM, but the SensL SiPMs have an additional and unique feature, the fast output. The standard silicon photomultiplier structure is modified slightly so that each microcell has an additional capacitively coupled output. The fast output signal is then the derivative of the internal fast switching of the microcell in response to the current flow from a detected photon. SensL SiPMs therefore have a third terminal for this fast output. And like the anode-cathode output, it's formed from the sum of all microcells, so the pulse height is also proportional to the number of triggered microcells. The plot here shows a typical output pulse from the fast output compared to one from the standard output from the anode-cathode line. The fast output signal is particularly suited to fast timing measurements, using the ability to clearly distinguish the arrival time of the first photon in the pulse. This concludes our introduction to the SiPM. But if you would like to know more, there is a wealth of information on the SensL website at sensl.com. There you can browse by product or application type. There is also a support section that features a large documentation library, an FAQ, a video page, and an academic research library. Thanks for watching.